Hey, good morning. Hope everybody's doing well. All right, awesome. We have a question in chat, which is, can you go over how to do the height function again? Sure. So the definition of height is, the depth of the deepest node, but we can code that recursively by doing something like this. So here's our function for finding the height of a tree with a given root. So the base case is if the root is null, return a -1. That's by definition the height of an empty tree. So this returns an int. So if the root is not null, then there is a left and a right child. Those might be null, but that's okay. Let's find the height of the left and the right children. So h left equals height of root arrow left, and h right equals the height of root arrow right. So that gives you the height of the left and right subtrees. If the left tree is higher, then return its height +1. Otherwise, return the height of the right subtree +1. And there you go. So if the root's null, base case, the height is -1. Otherwise, find the height of the left and the right subtrees by calling your height function. And then if the left tree is higher, return that height +1. If the right tree is higher, or the same height, return the right height +1. How is what number getting generated? Right here. And that's what's weird. That's one of the things that's weird about recursive functions, right? That's the only place that we actually return a particular value, and that's the height of an empty tree. But these other calls will return, some height +1. So if my tree has a height of 3, right, I'll end up calling the height function from every node in the tree. And when I call it from something that's a leaf node, it will call height on its null children, get back -1 from both of those, and it'll return -1 + 1 is 0. So our leaf node will come back and report a height of 0. And a node one level above that, right, say a node that's looks like this. Well, when I call the height function on the left subtree, it's going to return a 0. When I call it on the right subtree, it's going to return a 0. And so my height function on this tree is going to return 0 + 1, which is a 1. And it will kind of percolate all the way back up to whoever called the original height function on the original tree, and kind of automatically it will be the height of the tree. So when you call the height of root arrow left, right, that call will, at some point make a call to height of null. and that call to height will return a -1. But, you know, that will save -1 in some local variable h left, and it'll save -1 in local variable h right, and this will cause that call to height to return a 0. And everything is local. The h left and h right, these are local variables inside this height function, so they have their own value. And when I call recursively, and, you know, that height function sets its own values of h left and h right and bubbles down the tree and eventually sets those equal to -1, when I come back, my values are still what they were. It's a very peculiar thing to try to explain. And I think when I learned recursion, we wrote it by hand first. I may do that someday as an assignment. But yeah, so it kind of works. Well, it does work. It kind of just works. If you want to go deeper down a rabbit hole, look up something called Ackermann's function. I might have mentioned this in here before. It's an extremely recursive function, and I think it can only in general be calculated recursively. So that's an interesting function to look up and try to code. But we can do all kinds of things. Recursively. So let's say we wanted to print out the sum of integers. So let's write a function that returns the sum of the integers from 1 through n. Well, we could write a for loop. We could initialize a running sum to 0. We could loop, and we could add to that running sum. But we can write this function recursively also. I'll put in a base case. If we try to get the sum of integers from 1 to 1, it's just going to return 1. Otherwise, let's take the sum of the numbers up through n minus 1 and add n. So there's no obvious looping going on here, but this is a recursive way to think of the sum from 1 through n. It's the sum from 1 through n minus 1 plus an extra n thrown in. Right? And it works. And this is maybe an easier way to think about, you know, why doesn't everything get reset to 1? Because it's just a 2-line recursive function to play with. All right, so let's talk about fopen and such. So we know how to use fgets, right? So fgets, we normally use it to read from standard in, and so fgets buffer length standard in, then we can print that out. So if we want to read from a file instead of standard in, all we got to do is put an fopen statement and read from something other than standard in. So we declare our own version of standard in as a file star. It's uppercase file. And you usually see this called FP, so use this instead of standard in. And where should FP come from? Well, that's what fopen tells us. So we can say fopen, and let's open haha.txt, and let's open it for reading. So these are the two basic things you have to add. So file is a type of structure, right? It's typed after defined, I don't know which. But it's a thing that stores information about where to read. So yeah, it's definitely something special. So declare a pointer to an uppercase file, and then set that pointer equal to the return value from fopen. And now, instead of saying standard in, I can say FP, and I'll read from that file. Alright, so make a pointer to a uppercase file, set that pointer equal to fopen, name of the file, and then if you want to read from the file, inside double quotes, do an R. If you want to write to the file, do a W. If you want to read and modify, you can do R+, and so on. And in this case, since my character array is only 120 characters, I'm telling fgets read up to 120 bytes into my buffer. So it would be the first 120 characters of haha, or everything up to the first new line. And in this case, you know, my first line only has a few characters, so it should just read to that new line and then come back from fgets, just like standard in does. That's what happens when you hit an enter. You basically put a new line into your input stream. So if I run this, there's the first line of my file. And if I do this a few times, right, I can see the first 3 lines of my file, including my typo. And if I do this a bunch of times, I keep getting the same last line of my file once I hit the end. So if you look at the man page for fgets, this one right here, reads in at most 1 less than the size characters. Reading stops after an end of file or a new line. If a new line's read, it's stored into the buffer, and a null terminator is stored. Fgets returns S on success and null on error, or when end of file occurs. So we can tell if we've hit the end of the file by looking at the return value from fgets. That's not what I wanted to do. So I'm going to call fgets, and I'm going to check to see if it returns null, and if it does, I'll print out, hey, we got the end of the file. Alright, so it read my first 4 lines. That last line read normally, but the next time I tried to read, it said, oh, you're at the end of the file. So a typical way to do input from a file would be do something like a while loop. Right, so as long as fgets doesn't return null, let's go ahead and print out the contents of our buffer. And then we'll just print a message at the end. Oh. Thank you. You are absolutely right. There we go. Now, if you try to read a file that doesn't exist or that you don't have access to, then something different happens, right? We get a seg fault. Why do we get a seg fault? Well, take a look at the man page for fopen, and fopen opens a file, etc. Go down to the bottom for return values. Upon successful completion, it returns a file pointer. Otherwise, null is returned. So anytime you call fopen, check the return value and see if it's null. And here we'll just print an error message. Makes sense? Cool. I don't even remember what go.c was. Oh, that was recursion. Okay. Cool. All right. Oh, and fclose, yes. So when you're done with all of this, close your file. So what that does is basically release the resources that were used to open your file and make it accessible to you. And it does all the housekeeping that needs to be done at the end of file access. So this is kind of like, you know, ejecting your flash drive. Technically, if you don't close your file when your program exits, everything works great. You might get a valgrind error if you don't close it, actually. I did not. There might be a switch I can put on. Oh, wow. Nope, that's all good. So, if your program exits, your file pointers get closed and the resources get released. But if you don't do that, the file remains open. If somebody else tries to access it, there could be inconsistencies there. And if you write things to a file and you don't close it, those things that you write might not actually appear. Alright, so yeah, you do get a valgrind issue if you don't close the file. So keep doing valgrind, it'll keep you honest. All right, cool. Yeah, I was meaning to go over file access. Yeah, definitely a good catch. Thanks for catching that. All right, awesome. Other questions? Yeah, you're very welcome. Okay, just got to say I did not stay up until 2:30 in the morning last night playing with my circuit boards that finally arrived. Actually got to bed at like 2:20, so that was pretty good. But I actually got them built, and amazingly they seem to work, which is shocking to me so far, except for the chip that started, you know, venting its magic smoke. But I removed that chip and everything's better now, and I expected that one to blow up anyway. So, but I will post some things on this once I get it further along and get the top side built up, which is going to be 40 flashing lights and tons of switches and buttons and all kinds of things to entertain oneself. It's a Z80 based microprocessor that you can interact with directly through front panel controls, and write code and single step code and so on and so forth. And if you're curious, go ahead and take a look at, if you're not familiar with it, the IMSI 8080. That was one of the first commercial microprocessor systems available to hobbyists back in the 70s. And I cut my assembly language teeth on this thing, and it's a ridiculously fun platform to play with. And they are pretty hard to find now. They cost, you know, thousands of dollars if you can find one. But people make all kinds of clones, so I wanted to make a pocket-sized clone that I could, like, carry around on the bus or whatever. Not that I ride buses these days, but, you know. So I will post a link to the blog on it once I've got it up and running. All right, let's go back to sorting, and let's talk about quicksort. And quicksort is going to be our first recursive sort, and it's a very odd kind of algorithm to me, at least. It doesn't really have a feel to it like I know where it's going until we get there. But it's a very efficient sort. It has some interesting history behind it. So let's write down some numbers, and I tried to pick some numbers that I think will make an interesting quicksort example. Alright, so there's 10 numbers. Oh, you should always make cool stuff and show it off to random people. Absolutely. Alright, so we're going to sort from smallest to largest. Okay, so smallest over here on the left, largest on the right. And the way quicksort works, it's a series of passes. We're mostly going to concentrate on one pass. And when we make a pass, here's what we do. We pick a number called the pivot. And most common algorithm, you pick the number at the far right to be your pivot. And what we're going to do is we're going to rearrange things in this array so that when we're done with this one pass, the 17 is in its proper spot. In other words, we're going to put the 17 into whatever position it should end up in when the sort is finished, the whole sort. So if our pivot was 60, we would want the 60 to end up here. If our pivot was 1, we would want the 1 to end up here. If our pivot is 17, I don't know exactly where it ends up, somewhere around over here. I guess when we sort this, we're going to get 1, 8, 11, 12, 14, 14, and so I think the 17 should end up right here. Alright, so how are we going to figure out where the 17 should go without sorting the whole list? And there's an order n approach we can take to this. So order n, we're going to move this one number into its proper spot. And the observation to make here is that when 17 is in its proper spot, everything to the left of it should be smaller, everything to the right of it should be larger. Alright, so let's go through one of these passes and then we'll try to figure out why this works. So we could count the number of numbers that are smaller, but we also want to arrange it so that, you know, once we put the 17 here, everything over here is less than 17, everything over here is bigger than 17. So we've got a pair of goals. Right, one is putting this in the right spot, two is making sure everything over here is smaller, everything over here is greater. So we use a pair of pointers. The first pointer points to the first number, the second pointer points to the last number. We're not counting the pivot. Okay, we're going to compare to the pivot. So we start from the left, and we want numbers to the left of 17 to be smaller. So we look at the 12, and 12 is smaller than 17. So 12 is okay right where it is. So we move over one spot, and we look at 23. And 23 is bigger than 17. So it's got to go on the other side of things. It's got to go somewhere off to the right. Alright, so we're moving in from the left. And we're asking, are these numbers less than 17? We stop moving when we find something that's bigger. And now we start from the right, and now we're asking, are the numbers that we're finding bigger than 17? Alright, so 19 is bigger than 17, that's fine. Move in one more. 1 is not bigger than 17, so 1 should be somewhere off on the left. At this point, we've identified two things that are in the wrong spots. 23 should actually be somewhere off to the right, and 1 should be somewhere to the left. So we're going to swap these. And so now we're going to have a 12. Our 1 is going to come over here, 11, 14, 60, 55, 8. The 23 gets swapped with the 1. There's the 19, and this is still our pivot. And we've moved this far. Alright, so we started with the 12, decided that was okay, moved over 1, found that was in the wrong spot, stopped. Went to the right, 19 was fine, moved over here, 1 was in the wrong spot, stopped, did a swap. We're going to repeat that. We're going to go back to the left, and we're going to continue moving to the right. So we're going to look at 11. 11 is smaller than 17, that's fine. 14 is smaller than 17, that's fine. 60 is bigger than 17. That's a problem. So we're going to stop there, we're going to go to the right. We were at 23, we're going to look at 8. 8 is smaller than 17, that's also on the wrong side. And so we're going to swap these two. If you just started paying attention, you're probably lost, but we're going to do this a few times so you can pick it up next round. Alright, so after we swap, our numbers are going to look like this. And we've processed all of these, and we go back to the beginning again. So we had finished doing the 8, let's look at the 55. The 55 is on the wrong side. And over here we had done the 60, so we're going to move in one spot. And our two pointers collide at this point. So that's the end of our pass. And where those pointers collide, that's where the 17 should go. So now we're going to swap the pivot with that point where our numbers met. So the 17 goes here. There's 60, 23, 19, 55. And I'm going to circle this number that we just pivoted in. And guess what? We've achieved our goal. Our 17 is in the correct spot in the final list. Everything to the left is smaller than 17. Everything to the right is bigger than 17. So that's one pass of quicksort. And it's order n. If you have n numbers, right, I'm going to move to the right one number at a time. At some point I might start moving to the left. I might do a swap now and then, and I might move to the left, to the right, and to the left. But eventually my arrows will reach. And that will happen after I've compared, you know, roughly n numbers to my pivot and done a few swaps. So this one pass is order n. And the whole effort of quicksort is coding up this one pass, right? So this business of keeping a pair of pointers moving in, comparing to the pivot, swapping, and so on and so forth. Well, my list is not sorted. 60, 23, 19, that's not in sorted order. 12, 1, 11 is not sorted. But since everything over here is less than 17, and everything over here is bigger than 17, and 17 is in the correct spot, all I have to do now is sort this 5-element array and sort this 4-element array. How do I do that? Call my quicksort algorithm. So this is recursive. So the high-level view is something like this. So how do we quicksort data? Pick a pivot. Make a pass. And let's say our pass ends at location F, right? So swap pivot with, you know, that element that our arrows ended up at. And then quicksort the array from the first element to element F minus 1. And then quicksort the array from element F plus 1 to element N. Pseudocode, I'm not worrying about index 0, index 1 business. Alright, so make a pass to put one number in its correct place and leave everything to the left smaller, everything to the right larger, and then call quicksort twice. Once to sort everything on the left and once to sort everything on the right. And our base case, we always need a base case to get out of our recursive rabbit hole. If length of data equals 1, just return. There's nothing to sort if there's only one thing in our array. So yeah, what is the order of complexity of this? To do a single pass is order n. But once we've done a pass, we've split our set of data into two hopefully equal sized sets or close to equal sized sets. And we're going to continue doing this until we get down to an array of length 1, and then we're not going to recurse anymore, we're just going to return. So how many times do we have to cut in half in order to get down to something the length of 1? That's just log n. And you end up doing, you know, log n of these iterations, but each time you iterate, you end up having to sort twice as many arrays. So it feels like it's going to be, you know, an n squared proposition again. The trick is these passes get smaller and smaller each time that you go down your recursive journey, right? The first time that we do this, we might have 1,000 numbers to do this one pass on, and then we're going to have two arrays of length 500. Well, we've got to do sorts on both of those, but each of them is only going to be half the length. And in this case, if we pay attention to the constants, yeah, this will end up being a total order of n log n, ideally. So let's go through this process a few more times. Let's look at some other examples of this. And so I'll try to generate some numbers that will work. Doesn't have to be 10 numbers, obviously, but that's where my brain goes. Okay, so we'll start with 11 as the pivot. We'll begin from the left. This is smaller, this is smaller, this is bigger, so we're going to stop. We'll go from the right. We're looking for things bigger than 11. This is smaller than 11. We're going to swap these two elements. Now, I'll go ahead and rewrite this one more time. Obviously, you don't do this in code, but just to make it a little clearer. Okay, so now we start from the left again. We go to the 17. The 17's bigger, we stop there. We start from the right. 13's bigger, that's fine. 6 is smaller, so we'll stop there and we'll go ahead and swap these. So we're going to have a 4, 2, 3, 6, 8, 1, 17, 13, 15, 11. So we swap the 17 with the 6. Alright, we go back to the left. 8 is smaller, that's fine. 1 is smaller, that's fine. We get to the 17 and we've collided with our other arrows. So we stop the process right there, and now we're going to swap the pivot with where our arrows met. And this will give us our partially sorted list. So that's the pivot we just swapped in. And there you go. And then we would do the same thing on this sublist. And once we sort this, we would do the same thing on this sublist. And once we've sorted both of those, the whole list will be sorted. This kind of thing works really well on, say, a multi-core architecture. If you have two cores in your CPU that are both available, they can both work on, sorting each of these sublists simultaneously. There's no interaction between this part of the array and that part of the array. There's nothing over here that's going to get moved over here or vice versa. So I can have two CPUs running my quicksort algorithm on these two chunks of data, and they will be able to work completely independently, perfectly parallel. And on the next pass, when I split this into two more sublists, if I have 4 cores, all 4 of those can be working very efficiently. Second pass, sure. So let's go ahead and sort this. So what does this look like? There's 4, 2, 3, 6, 8, and there's our pivot 1. And so we'll start here, and this is in the wrong spot because it's bigger than 1. And so we'll come here and we'll look for things that are smaller than 1. This is fine, this is fine, this is fine, this is fine. We come here and we've had a collision. So we know that the 1 should go in this location right here. So this would become a 1, 2, 3, 6, 8, 4. And now this is in the correct spot. So now we would sort the sublist on the left, which is null, and we would sort the sublist on the right. And similarly, we would take this list and we would break that into, 13, 15, 17. This would be our pivot. This is smaller, so that's fine. This is smaller, so that's fine. And we're out of stuff. Well, if we go all the way to the right and we don't encounter any arrows, then the pivot's already in its right place. So now that's in the correct spot of this subarray on the right, and now we have to quicksort 13, 15. Now, quicksort is this quirky, has this quirky characteristic that if your data is pretty close to sorted to begin with, quicksort does not perform well. So, for example, right? Suppose this is your data that you want to sort using a quicksort. So we'll start off with this being the pivot, and looking for things that are smaller than 19. This is fine, this is fine. All of these are going to be fine. We're going to run out of things that tells us the 19 is in the correct spot. And now we split this into two subproblems. First, we have to sort this null right sublist, which has nothing in it. And our second problem is to sort the sublist on the left. So now we have to sort 2, 3, 5, 7, 11, 13, 17. And when we do that, we're going to find that this 17 is in the correct spot, which means the next time we're going to sort this sublist, which is one element less in length. And so if your data is sorted to begin with, what you're going to find is that, one pass is order n, but you're going to end up doing approximately n passes. And this will come out as n squared. And so here's a weird thing to think about in daily life. You can sort this more quickly if you start off by randomizing the data, which is interesting to me. So a lot of times quicksort algorithms will start with a pass that jumbles up the data, just in case it happened to be close to sorted to begin with. And by randomizing it, it actually does a better job of sorting. If it's already sorted, then you get this behavior where each time that you do that one pass, your subproblem becomes only one element less. So we were trying to sort an array of 8 numbers. We did one pass of quicksort, found that the 19 was in the correct spot, and now we have to sort a list containing 7 numbers. And after one pass of quicksort, we'll find the 17's in its correct spot, and we'll have to pass a 6-element array to quicksort. And so we're going to end up doing this a total of n passes, and each pass is going to be average, n over 2 operations. So yeah, exactly, that goes back to n squared instead of n log n. All right, questions about that? So definitely try this, right? You can find all kinds of things online to read about this, but just make yourself some data. Don't make it sorted. Right, just make yourself some data and try doing a few passes of quicksort. Don't sort sorted data. Yeah, exactly. And you can make the pivot anything, but the most common case is to make the pivot the rightmost thing. And just do this exercise. You know, start from the left, find things that are smaller. Oh, I picked a bad pivot. Stop when something's bigger. Start from the right, look for things that are bigger. Stop when something is smaller. Swap those. Continue until your arrows hit. And then swap with where those arrows met. And when you're done with that, and you've put a box around the pivot that you just swapped into its proper place, everything to the left should be smaller, everything to the right should be bigger. That's a 1, 3, not a 13. And it's pretty confusing, I think, to listen to an explanation of it. To me, it's more confusing to read an explanation of it. It's less confusing to actually just do it and go back through the videos or look at some of the animations on the wiki page or whatever and figure out how this works. We're not going to code this, okay? This is fairly tricky to code in C because of the way arrays work. Dealing with this stuff that's so easy to write in pseudocode, quicksort data from f+1 through n, that's all kind of a pain to do in C. But make sure you understand the algorithm, right, to move your pivot into the proper spot. And just play with some sample code and work on that and ask questions in class or office. All right, so tomorrow we'll do merge sort, which will be another n log n sort, and that one's a lot easier to understand. And then we'll talk about radix sort, and then we'll talk about heaps and heap sort, and that will probably do us for sorting. All right, cool. Have a good one. I will see you tomorrow.